In this video, we're going to look at redox reactions involving functional groups that contain heteroatoms. So recall heteroatoms are any atom besides carbon and hydrogen. So in this case, we have an alcohol. More specifically, we have a primary alcohol, and we know that because we can identify where that alcohol functional group is located to identify the alcoholic carbon, and we can see that there is only one carbon atom directly bonded to it. So I'll just go ahead and redraw this just to show the expanded form of the atoms that are present. So the carbon all the way to the left has 3 hydrogen atoms, and we know that because it only has one bond. So there are 3 hydrogen. This next carbon has 2 bonds, so 2 hydrogen. And then you have that last carbon that has the OH bonded. We can see the 2 bonds, so we know it has 2 hydrogen. So if we have this primary alcohol and we're performing a redox reaction, so because we have the O in bracket, that tells us that we're adding an oxidizing agent to this alcohol. Recall, oxidizing agents are not oxidized, but instead they cause something else to be oxidized. So adding an oxidizing agent is going to cause that alcohol to become oxidized. In order for alcohols to become oxidized, so this applies whether it's primary, secondary, and you'll see tertiary as well. In order for the alcohol to be oxidized, you want to locate your carbon-oxygen bond. And so when you see that OH, that is the same thing. It's saying that there is a bond between that oxygen and hydrogen. So I'm going to just go ahead and expand that. You don't have to expand it, but I'm going to just expand it for this example. But when you're trying to oxidize your alcohol, locate your carbon-oxygen bond where your alcohol is bonded. So in other words, in this case, I'm boxing off my oxygen and my alcoholic carbon. Once you box off that area, check to see if both ends, so in other words, that oxygen and the carbon, if both ends contain a hydrogen. If they do, oxidation can occur. So I'll redraw this because I have both ends containing that hydrogen. I didn't do anything to these carbon atoms. So carbons 2 and 3, nothing happened. But around carbon 1, since both ends contain that hydrogen, those 2 are now being removed. Just imagine that the half of bond remaining between the carbon and the half of the bond remaining between the oxygen, they now fold down to create a whole bond. So instead of those 2 half bonds, we now have a whole bond, an additional whole bond between that carbon and that oxygen. So we now have a double bond between the carbon and the oxygen. We still have that other hydrogen. So we've gone from a primary alcohol to now having an aldehyde. So primary alcohols are oxidized to give an aldehyde. You see a change in that functional group. However, aldehydes can also undergo oxidation. So when looking at your carbonyl containing groups, to determine whether or not they can be oxidized, look to see whether or not the carbon of the carbonyl, whether or not it has a hydrogen. If it does, now instead of losing the hydrogen, because recall, oxidation of organic compounds can represent an increase in oxygen or it can represent a decrease in hydrogen. So we just saw the decrease in hydrogen. Now what you will see is an increase in oxygen. So you're not losing your hydrogen, but now an oxygen is simply being added to that molecule. So it's almost as if, just imagine that oxygen is now being inserted between the carbon of the carbonyl and that hydrogen. So that's where our hydrogen was originally located, but we still have the hydrogen. We just inserted that oxygen. So now we've gone from an aldehyde to a carboxylic acid. So we still have a carbonyl containing group, but we no longer have a hydrogen directly bonded to the carbon of that carbonyl. So no further oxidation will occur. So the process of oxidation. If you start with a primary alcohol, it can be oxidized to an aldehyde. Aldehydes can be oxidized to carboxylic acids. If we went in the reverse direction, so if we went from this carboxylic acid to that aldehyde, that would represent reduction. So a carboxylic acid can be reduced to an aldehyde. The aldehyde can then be reduced to the primary alcohol. So that takes care of primary alcohols. But we know not every alcohol is primary. So let's see what happens if we have a secondary alcohol. So if I have that secondary alcohol and I want it to become oxidized. Again, it's secondary because we can locate that alcoholic carbon, which is the carbon that the OH is bonded to. In this case, it's directly bonded to 2 carbon atoms, making it secondary. So I'm going to still show it as the expanded form. So that first carbon, 1 bond, so there are 3 hydrogen. Second carbon, it has 3 bonds because you have the OH. You have the 2 carbon, so therefore it has 1 hydrogen. And then that third carbon, we can only see 1 bond, so we know that it also has 3 hydrogen. So again, I'm just going to expand this oxygen hydrogen to show the actual bond. And remember, when looking at an alcohol, regardless of whether primary, secondary, tertiary, look for that carbon-oxygen bond. So I have my carbon-oxygen bond. That includes your alcoholic carbon and the oxygen from your alcohol functional group. Make sure each end, so make sure that carbon and that oxygen each have a hydrogen. So I still have that in this secondary alcohol. I didn't do anything to carbons 1 and 3, so those carbon atoms are still the same. They each still have 3 hydrogen. But carbon 2, I still have a bond to that oxygen. However, when those hydrogen atoms were removed, they each took half of the bond. So the carbon and the oxygen both had half of a bond remaining that could then form a whole bond. So you end up with a double bond between the carbon and the oxygen. So we've now gone from a secondary alcohol to a ketone. Recall, once you form your carbonyl containing group, you need to look to see if it has a hydrogen. But of course, in the case of a ketone, it doesn't. It only has 2 carbon groups. So if we were trying to oxidize that ketone, so I'm just going to redraw it. So this was the ketone formed as a result of the oxidation. If I wanted to oxidize this ketone, no reaction would take place. So RXN is the abbreviation for reaction. So ketones cannot be oxidized. Secondary alcohols can be oxidized to a ketone, but they can't be oxidized any further. However, that ketone can undergo reduction to form the secondary alcohol. So the ketone can be reduced, but it cannot be oxidized. And so we've seen that the primary alcohol can undergo oxidation to an aldehyde, which can be further oxidized to the carboxylic acid. We've now seen where the secondary alcohol can be oxidized to give a ketone that cannot be further oxidized. So let's now look at the tertiary alcohol. Look at that oxidation process. So again, I'll draw this in the expanded. And so you have, this one may be a little trickier for you to see. We have a total of 1, 2, 3 carbon atoms, or 1, 2, 3 carbon atoms. I have my 1, 2, 3 carbon atoms. Those two carbon atoms on the end, carbon 1 and carbon 3, they each only have one bond, so they each have 3 hydrogen. From there, the carbon 2 has a methyl group, so it has a carbon that has 3 hydrogen. And then it also has that hydroxyl. So if we're trying to look to see whether or not or how this would be oxidized, again, because it's an alcohol, we want to locate our carbon-oxygen bond. So the carbon of our alcoholic carbon, the oxygen of our alcohol functional group. From there, we want to make sure they both have a hydrogen. So the oxygen has the hydrogen, but the carbon only has carbon attached. I can't lose those 2 hydrogen in order to form that double bond. There's no bond that I can lose around that carbon that would allow the double bond to form, so therefore no reaction would occur. Tertiary alcohols will not be oxidized. So primary and secondary can undergo oxidation, but tertiary alcohols cannot undergo oxidation. And so here it shows how you can convert and go between those different functional groups. So we've looked at the different alcohols, so let's just look at one example, just to make sure you're able to apply this. So let's say that you were given the following structure. Let's say you had this compound. Let's say you were asked to react it with a reducing agent. So if you're reacting this compound with a reducing agent, that simply means that you are reducing this aldehyde. So think about how aldehydes are reduced. So think through the process. What alcohol was oxidized to give an aldehyde? Of course, it would be the reverse reaction if we're now looking at reduction, because now that would indicate that that aldehyde will be reduced to give that same alcohol. If you couldn't remember that, you can go through the process of doing the reduction. Hydrogenation, so adding hydrogen, is the most common method of reducing an organic compound. So just as we saw when we were oxidizing, we had to remove those hydrogen. Reduction is the exact opposite. So instead of removing those hydrogen, we would now add those hydrogen. In order to add the hydrogen, we would have to break a bond first. So we would simply break the double bond. It's going to be the most reactive bond. So instead of 2 bonds between a carbon and oxygen, we would only have 1. However, this carbon has now gone from having 4 bonds around it, so 8 electrons, to only having 6. This oxygen, even though we didn't draw the non-bonding electrons, they're present. That oxygen has gone from having 8 electrons around it, so they're still present, to now only having 6. So each atom, that carbon and that oxygen, have both lost electrons. So that old bond broke so that the new bond could then form. When adding hydrogen, remember hydrogen is a diatomic molecule. So even though we simply say hydrogen, we know we're adding H2. So we're adding 2 hydrogen. Both ends where the double bond was located. So the carbon and the hydrogen, they'll both gain a bond to a hydrogen. So that carbon and oxygen will both gain a bond to that hydrogen. So if I redraw this compound, so I have 1, 2, 3, 4. 1, 2, 3, 4. Attached to that 4th carbon, I can show it up, I can show it down, it doesn't really matter. But just to keep with the same direction, I'll just go ahead and show it up. I have that OH. I don't have to actually show the OH here because I know that this carbon has only 2 bonds that are shown, so therefore there are 2 hydrogen that are not shown, which will represent those 2 hydrogen. So reducing the aldehyde should give you a primary alcohol, which we do have. What if I wanted to oxidize that aldehyde? Recall aldehydes could undergo oxidation. Because that carbon of the carbonyl has a hydrogen, it can undergo oxidation. So remember, we're simply inserting an oxygen between the carbon of the carbonyl and the hydrogen that's already there to give a carboxylic acid. And so if you're trying to show the product of the reduction, simply think of what would happen if you're adding hydrogen. If you're doing the product of oxidation, it depends on whether you're starting with the alcohol or you're starting with the carbonyl containing group. If you're starting with the alcohol, locate the alcoholic carbon, identify that carbon-oxygen bond, make sure that both ends, so in other words, the alcoholic carbon and the oxygen, make sure they both have a hydrogen. If they do, oxidation can occur to form a carbonyl. If they do not, oxidation cannot occur. If you're starting with a carbonyl containing group, as we have here, check to see if the carbon of the carbonyl, if it has a hydrogen. If it does, the oxygen will simply be inserted between the carbon of the carbonyl and that hydrogen. If it doesn't have the hydrogen, oxidation will not occur.